Okay, actually, we're usually not up today, not this week. We'll reconvene next week. Don't forget you have a quiz due today at 5 o'clock, and after the quiz is due, then I will post the next quiz as usual, Tuesday at 5. Okay. Questions? All right, so what we're going to talk about today is coordinate systems. A coordinate system is a way to write any vector in a vector space in terms of bases. Now, if I get different bases, then maybe I have to give different coordinates. So let me start off with a simple part of this. So we'll call this the unique representation . Now, last time and earlier as well, I gave you all sort of a hint about what this is all about. And this is kind of an important thing. We'll go through why this is true here. So let's let fancy B be a collection of vectors, and I don't want just any vectors. I want it to be a basis to the vector space B. Now, somebody remind me, what does it mean for these vectors B1 up to Bn to be a basis for the vector space B? Right, two things. These are linearly independent. And number two, all the crap in B is a linear combination of B, right? So everything's a linear combination. So here's what this theorem says. Then for all B in capital B, there is a unique set of scalars C1, C2, Cn, such that it's a linear combination of these. Let me write this here. So here's a notation. If B is equal to C1 B1 plus C2 B2 Cn Bn, and sometimes right. So when you see this notation right here, what this means is I'm reading these coordinates with respect to the basis B. And what does that mean? That means that C1, C2, Cn are the respective multipliers of B1 up to Bn that create your B. Everybody okay? That's kind of a notation to use. Now, what does this theorem here really say? Well, it says if you have a basis, then any V in here can be written as a linear combination of the bases. That's not new. That's something we know, that anything in the vector space is a linear combination of the bases. What is new is this. So yes, I can find some C1, C2, Cn that make this V, but there's only one way to do it. That's what the uniqueness means. Only one way to do it. And this is so important that I have to show what this is. So let B be something that lives in the vector space. I want to show that there's only one way to write it. So suppose that we can write B two ways. Suppose we can write B as C1, B1, C2, B2, plus CM, B. And suppose I could write it another way. I don't know, we'll say B1, B1, plus B2, B2, plus B. Suppose I could write it two ways, right? And in fact, let me give you kind of a little fun fact. If your set is linearly dependent, you can actually write it infinitely many ways, right? Well, let's just suppose that I can write B this way with the coordinates C1, C2 up to Cn. And I can write B also with different coordinates, D1, D2 up to Dn, all with respect to base B. Anybody smell what the rock's cooking here? And what's the next step? Let's subtract this, right? So these are two ways to write B, right? So let's subtract because I know how to subtract. So B minus B is, of course, the zero factor. And what do I get when I subtract this side here? Tell me if I don't go too quick on this, but everybody see how I got this? This minus this, C1 minus D1, this minus this, C2 minus D2, minus D2. So everybody okay with that? Wrap your eyeballs around that and tell me what's important.
C1 or all the C have to equal all individually so that the coefficients are zero.
Okay, so your claim seems to be this, 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 all have to be zero. And he's correct. Why? What is it? What fact about what factoid am I using to guarantee control zero?
The fact that the basis is zero.
That is correct. That's the one thing that we haven't used yet. A basis is a linearly independent set. This is true because B1, B2, Bn is a basis. So linearly independent. Every one of these coefficients has to be zero because you have a linear combination of bi's being zero vector. All the stuff that's multiplying has to be zero. Okay, so far? And so to finish this up, this means C1 minus D1 is zero, C2 minus D2 is zero, all the way up to Cn minus Dn is zero. And so what does this mean? This means C1 equals D1, C2 equals D2, all the way down to Cn. And so we see there's only one way to write it. Because these have to be equal, these have to be equal, all the way down the line. This is one of the reasons that linearly independent sets are so important. When you can write something as a linear combination of a linearly independent set, there's only one way to do it. And when you're solving problems in science and engineering, oftentimes you get basis representations. And when you know that it's linearly independent and you get a solution, you know you're dealing with the only solution, which is always important when you're doing STEM type problems. Okay, any questions? Yes, sir.
If they're literally independent, why is that mean that C1 minus D1 has to be 0?
Because what this is this is A1, call this A1 and A2, AN, right? This is number times B1, number times B2, number times Bn. But remember, when you have a linear combination of B1, B2, Bn,
Okay.
all the coefficients have to
Yeah.
be 0.
Okay, that makes sense. Thank you.
Everybody okay? Okay, so I kind of alluded to this a little bit, but let me give you this definition sort of formally. Definition. Yeah. Fancy V is a basis. Well, okay, so suppose we have a base B, and suppose B is in B, so this little b is a vector in B. Then the coordinates of B relative to the basis fancy B are the numbers C1, C2, Cn, such that so these numbers here are what we call coordinates relative to this basis. So if I give you a basis, if I walk up to you on the street, give you a basis, B1 at the end, then that means that every vector B that lives in the space can be written as a linear combination of this basis. These numbers that you need, so these numbers sort of help you adjust to get what B is. These numbers are what we call the coordinates. And the previous theorem says this is a well-defined thing. If I say the coordinates, they're unique. Okay. So, let's see here. By the way, just for giggles, before I get carried away with the coordinates here, I wrote that statement up there without any support. I just said, okay, look, here's a basis for R2. Can somebody tell me how I know it's a basis for R2, or perhaps how to find out? Yes, some.
So since it's only 2 vectors and they're like, well, I guess it's the vectors. then if one's not a multiple of the other, it's, you know,
That's terribly clever. I unfortunately only work for two space, but why not? I mean, I did give you a two-dimensional space, right? Then y'all get this argument, says, look, one vector is not a multiple of the other, so they must be linearly independent. And since there's two of them, it must span all of them. Can somebody give me a more general approach that I could use with this to quickly tell the spaces? Yes. Right. Throw these bad boys in a matrix, right? And then do row reduction. What are you looking for to make it a basis of R2? That's right. You should be able to get the row reduced echelon form. You should be able to reduce it to the identity matrix. And in this case, you can, because it's fairly easy. If you had -1, imagine that's a matrix. -1 of this times this, you're going to get a 0 here and -2 here. So it's got two pivot columns. So you're going to be good. Everybody okay? So it is a basis. But what I want to do here is I don't know, we make some kind of 5, 8, and 7. Find the standard coordinates. Okay, all we got to do really is take apart what this means. This is really kind of to illustrate the vision. So what we have is we have vector B in terms of this basis B is what does this notation mean? What does this notation here mean? This means 5 times the vector B1 plus -7 times the vector B2. So in our situation here, so this is, what is this? 5 minus 7 is -2. 5 plus, I'm sorry, I'm totally on drugs here. There we go. This is 5 minus 7 is -2, and this is 5 plus 7, which is 12. And what I mean by standard coordinates is -2. So in other words, this vector B, so we see it's got different coordinates for different choices of basis, right? So in standard coordinates, I could write that as -2, 12, and I know exactly where that is in the XY plane. It's -2 and then 12 up. That's the same thing as 5 times 1, 1 minus 7 times 1 minus 1. Okay. Let's do kind of another one in spaces. Let's do this kind of geometrically. And I'll take this one with all positive. Let's say you kind of look at this here. This representation in the B coordinates is what is this in standard? So what I mean here is C is 2 B1 plus 3 B2. And we can actually sort of see this one geometrically here, and we can work it out algebraically by hand. So B1 is vector 1, 1. And B2 is vector 1, negative. And really what this is saying is give me two B1s. So we've got another one here. And give me three B2s. Maybe like that. And add them up. And you can do this via the parallelogram law, and this parallelogram is really nice rectangle. So that makes it roll that out a bit. It should actually be this vector right here. And let's see if that makes sense with mine. This is actually 2 times vector 1, 1. Plus 3 times vector 1 minus 1. So this comes to the standard coordinates, 5 minus 1. Okay, so that looks ballparky. Okay, let's do this the other way. See if y'all can help me figure out how to do it the other way, as a matter of fact. So what have I done so far? I had started with B coordinates, something that I made gotten the standard coordinates out of, right? What if I wanted to work the other way? What if I wanted to start with something in standard coordinates and get it in terms of something else? So let me pick up an example here. Let me take up a couple of the basics. Let's let B1 equal the basis 1514. And let B2 be 4332. Again, I'll leave it as an exercise for y'all to sort of verify that both of these are in fact bases of R2. You can put these both in a matrix here. This one 1154, this one 4332, and you can do Gaussian elimination and show that you can row reduce this to the identity matrix. But for these examples, I like Simon's argument even better in the sense that these two vectors are not multiples of each other, so they must be linearly independent of their basis or in both cases. But here's what I want to do. I want to take my original vector here, my standard over 2 up 3, and I want to write this. I want to express this in terms of this. Yeah, how do I do that? Right? It was easy enough to go in the forward direction, but how do I stick it reverse? So let me give you some general instructions here. Let's find this in B1 coordinates and then B2. Okay, well, so how do I do that? Ooh, I've got an idea. How about splitting around? Because what are we trying to do actually? We're trying to get T3 or V, well, as, let's say X times that's what I'm trying to do in both cases. So for B1, let's do this here. What we have is equation 2, 3 is X1 times 1, 5 plus X2 1, 4. That's really what we're doing. So what is this? It's a breaking system of linear equations again, right? That is 2 is X1 plus X2, and 3 is 5X1 plus 4X2. We put this in an augmented matrix. 1, 1, 5, 4. I want that to be 2. So all we got to do is row reduce. And this is 0, minus 1, and what I multiply that by minus 5, so minus 7. Yes. And I will take one more step in Gaussian elimination here, because it's so easy to do. This is going to be 1, well, 0 minus 1 minus 7. Just add this up here, 1, 0 minus 5. These are easy equations for me to deal with. This first one is X1, -5, and X2 is 7. By the way, somebody explain how I can check this, right? Like I said, and in math in general, and this course certainly, there's lots of ways to check things. How can I check it? Yeah, you still look back into your original thing, you notice that -5 times 1, 5 plus 7 1, 4 equals, let's see, that's going to be 2. Good. -25 plus 28 is 3. So if I write V1 coordinates, V is equal to -5. So the V2 is essentially the same. Basis now is 4, 3. 3, 2. And procedure you go through is exactly the same. What you want is you want vector B, which is 2, 3, be X1, 3, plus X2, 3, 2. By the way, so here's kind of an application. This is a little bit, what if this, can somebody tell me quickly, what the answer would be, if this instead of 3, 2 was 2, 3. 0 and 1, everybody agree? If this was 2, 3, 2, 3 is easily 0 and 1, and that's the only solution because basis has a unique solution, right? But this is 3, 2, so there's a little more here. So again, the augmented matrix is 4, 3, 3, 2. So I'm going to do my little trick again because let's avoid doing fractions because I'm a lazy man. So let me first just add negative the second row to the first, just to make that a 1. Minus this times this, minus this times this, minus this times this. 3, 2, 3. And now I can use this to take out the bottom. 1, 1, minus 1, 0, minus 1, multiply by 3, multiply by 3, that's going to be 9. And I'll do one more step, it's easy to do. I'll leave the bottom alone. Just add up here. That's where you do things. So what I get here is x2 equals -9, and x1 is equal to 8. So what this means is 2, 3 is the vector 8, -9 in our second phase. And again, you can check this because this thing is really what this means. This is 8 times 4, 3 minus 9 times 3, 10. And so this comes to 32 minus
The first matrix, you should have, or,
okay, so what did I do?
you added 6 to the next matrix then, instead of adding 3.
Yeah, it should be 1.
So from here to here's my mistake.
Yeah, 9 6.
Okay, so that would be, oh, that's 6. That look better? Good thing I checked myself, huh? Right, because that caught it. So, so this step right here should be adding up here. This will be 5, and this will be 6. Yep, much better. So this is going to be, let me just kind of strike this out. X2 is in fact -6, and X1 is 5. So let's check that. So on the second basis, five minus 6 and we'll check this one out, just to make sure I didn't hit it again. And this time I get 20 minus 18 is 2, and 15 minus 12 is, okay, so I got it. Any questions? Yes, ma'am.
First.
This right here.
Yeah, from there to there.
Right here. Oh, right. Really, to do this, I should divide by 4, divide by 3, right? Which I didn't want to work with fractions. So to make my life easier, I took -1 times this and added it up here. And the reason is to turn it into 1. It made I don't have to make any fractions. You don't have to do that. I just did it. Okay, other questions? Let me make an observation here. Um, we're gonna do a more full treatment of this as we progress. But here, what I'm gonna do is I'm gonna tell you how to change B coordinates to the standard coordinates. And there's a matrix for this, which might not be surprising. So, suppose we have um, suppose we have a basis for our answer, right? We've done a bunch of examples of this today where we had bases bar two, we had standard bases, we had basis 1514, we had basis 4332, 11, 1 minus 1, etc. So suppose you have standard bases here, and these are, or suppose you have a basis. With the matrix, this is I'll call it E, D. So if you take this basis and take and make columns of matrix, this is an in-line matrix here, of course. Change this. This matrix always changes B coordinates to standard. This, I want to make sure we wrap our heads around this. So let me do an example and show you why it works this way. So, example. Let's let B be the basis. 1, 5. So in this case, we have this. Now, let me point out, so I'm going to write stuff down here that sometimes I'll express later. What is 1, 0? What does this notation mean in B coordinates? Well, it just means that this is 1 times this and 0 times this, right? Now, when I multiply this by this matrix here, what happens when I multiply? This row from this column 1, this row from this column 5, and this is the standard coordinate representation. So if I'm talking about the basis B, if I say 1, 0, I mean this and 0 of this. If I say 0, 1, I mean 0 of that and 1 of that. If I say in B coordinates 2, 3, I mean 2 times this plus 3 times this. If you look at PB times 0, 1, 0, 1, of course, means the vector 1, 4, And let's see what happens here. This one from this column to one, this one from this column to four. And standard. So when you put in the columns of the basis, that changes basis B coordinates to standard coordinates. And more generally, if you look at 1, 5, 1, 4 times any vector, this will translate exactly to what you think it is, right? Because what this is this becomes the vector, let's see, A plus B, and then it gets 5A plus 4. Right? Right, what do you see from? And you can break this up as A over 5A, B and 4B. And now I can jerk out an A. And this is exactly what this means. This notation means A times the first basis vector and B times the second basis vector. So does everybody see why it works that way? Why this matrix changes B coordinates into the standard? Everybody okay? Okay. There. Let's let B B1 B and B then function takes B to B is a 1-to-1 onto linear transformation B. So this is sort of the big centerpiece of the last part of the class. And that is this. So what is it saying? Notice this can be any basis of any vector. Right? The only sort of restriction here is it's an n-dimensional space. You need n of these spaces. Let me give you an example of something that's not Rn. Right? You can look at 1x squared. We saw last time that's a basis of p2x, right? Polynomials of degree 2 or less. Y'all remember that? That is a basis with 3 elements in it, 1x and x squared. If you take that, if you take anything that's a linear combination and read its coordinates off in that basis, then that vector is now a vector in Rn, in our case R3. And this linear transformation, 1-to-1, and it's onto So it's like prom night. Nobody's jealous and everybody's got a date, right? And it's a linear transformation. What this basically says, basically, is if you have an n-dimensional vector space, it is the same thing as Rn. Almost. It's isomorphic. You can pair things off. So why does this work? So we'll find T on B. My input is any old vector that's a linear combination, and my output is its coordinates. Let me show you how this works. B is written uniquely as C1, B1. Tell me what my output is.
A vector that starts with like C1 and C2. So
Exactly. The way this function works is it takes this input vector V and it writes V out. Because remember, you can write V in terms of the basis and there's only one way to do it. All right? So given that V, ding, 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 I know exactly what these coordinates are. And what this function does is it just reads the coordinates and puts them in a stack over here. Right? This is a linear transformation because if you look at C of C1B, T of Cn Bn plus D1 B1 Dn Bn. Well, first thing you got to do is reorganize this. And so I would reorganize this way. C1 plus D1 D1, C2 plus D2, D2, Cn plus Dn, Dn. And then the rule of my function says, hey, Jim, read your coordinates and stand them up in one of these things. But now I can break this up. Because that's how you write vectors, right? You can break them up this way. And this is the same thing as T, C1, B1, Cn, Bn, plus T of D1, B1, Dn. So they're part of it. Also, you get the scalar multiplication fairly easily. Lambda C1 B1, lambda C1 Bn, which is lambda C1, lambda C2, lambda Cn, and lambda C1 Cn, lambda T C1 E1, Cn. What's the linear transformation? Now, let me finish this off by saying, why is it 1-to-1? Somebody explain why it's 1-to-1?
In this case, I just said there's no two different ways to do the same exact thing.
That's right. What it needs to be 1-to-1 is no two different ones of these go to the same one over here, right? And the reason this is true is because you have uniqueness of representation here. There's only one way to write this, right? And so it has to be 1-to-1. And it's clearly onto, isn't it? Because make up any string of numbers you want here, any n numbers, and just build this thing that goes through it, right? So this is 1-to-1 and onto. So For example, you might do just for fun. So for example, there's a one-to-one and onto linear transformation from P2S to R3. Just read the coordinates using the basis 1x and x squared and see where they go here. And so basically, all degree 2 or less are the same thing as R3. Okay, any questions? Any questions? All right, don't forget your quiz at 5. The next one will be posted after you turn it in. And other than that, y'all have a good weekend. We'll see y'all Monday.